What if gravity isn't just a force that pulls, but also one that can push? For centuries, Newton's and later Einstein's ideas shaped our understanding of gravity. An apple falls from a tree. The moon orbits the Earth orbits the sun. Gravity, the universal glue, holds it all together. Newton's equations predicted planetary motion with stunning accuracy. Einstein reimagined gravity as the curvature of space-time, explaining mysteries Newton couldn't. But what if that's only half the story? The Cosmic Repulsion Principle, or CRP, suggests gravity has a hidden repulsive side that emerges on cosmic scales. This isn't a minor tweak, it's a radical rethinking of the engine that drives the universe. The puzzle begins with a mystery. When we observe galaxies, the stars on the outer edges move far too fast. According to gravity as we know it, these stars should be flung into space. But they aren't. They hold stable orbits. Either our understanding of gravity is incomplete, or something invisible is providing extra pull. For decades, scientists have searched for this missing mass. But as the search comes up empty, we're forced to reconsider. Maybe gravity itself needs a second look. Perhaps gravity has a secret, a repulsive side that creates a new kind of cosmic balance. This is where our journey begins. Picture a spinning carousel. Horses near the center move slowly. Those on the edge race around. Now imagine a galaxy, a vast spinning disk of stars, gas, and dust. Most visible mass is near the center, so by Newton's laws, outer stars should orbit more slowly. But in the 1970s, astronomers like Vera Rubin found the opposite. Outer stars move just as fast as those near the center. The galaxy rotation curve, orbital speed versus distance, stays flat, not dropping off as expected. This was a shock. The outer horses kept pace, defying physics as we knew it. The discrepancy was huge. Visible matter alone couldn't account for the speeds. Gravity's laws, so reliable in our solar system, seemed to break down on galactic scales. The flat rotation curve became a defining mystery of modern astrophysics. It signaled our cosmic inventory was incomplete. Were we missing hidden assets, or were the rules themselves wrong? This single graph forced us to confront the possibility that we don't understand the universe as well as we thought. The search for an explanation began, and it would change everything. To solve the galaxy puzzle, astronomers proposed a bold idea: dark matter. This invisible substance, undetectable by light, would form a vast halo around galaxies, providing the missing gravity. Dark matter saved our cherished laws of gravity. No need to rewrite Newton or Einstein, just add a new ingredient. According to this model, normal matter is only about 5% of the universe. Dark matter, 27%. The rest is an even stranger dark energy. For decades, physicists built sensitive detectors and ran massive experiments, searching for dark matter particles. But despite all efforts, we found nothing. No direct evidence, no particles, no signals. The ghost remains a ghost. This persistent failure has led some scientists to question the entire approach. What if the solution isn't invisible matter, but a new understanding of gravity itself? The lack of detection has opened the door for alternative ideas. Maybe it's time to look in a different direction, and that's where CRP enters the story. Sometimes revolutionary ideas come from unexpected places. Enter Rohit Roy, an independent researcher with a fresh perspective. Roy didn't search for missing matter. He questioned gravity itself. What if gravity isn't always attractive? In physics, forces often come in pairs. Why not gravity? Roy proposed that under certain conditions, gravity could become repulsive. This was the foundation of the Cosmic Repulsion Principle, or CRP. Unlike Einstein's constant repulsion, Roy's force is dynamic. It awakens based on how matter is distributed. In places like our solar system, it's negligible. But in galaxies, it could be crucial. CRP offers a radical alternative. Maybe the weird galaxy behavior is just gravity's hidden side. The theory was born from curiosity and independent thought. Sometimes the biggest breakthroughs come from asking the simplest questions. How does CRP work? It's all about how mass is spread out. CRP introduces a repulsive force that arises from steep changes in mass density. Think of it as a gradient. In a galaxy's dense core, gravity pulls inward. But as density drops off toward the edges, CRP predicts a repulsive force pushing outward. This push weakens gravity's net pull in the outer regions. The result? Outer stars can maintain high speeds without flying off, solving the flat rotation curve mystery. Unlike dark matter, CRP doesn't add invisible mass. It changes the gravitational equation itself. It's a more economical explanation. No need for undetectable particles. Gravity can both pull and push, depending on the cosmic landscape. The universe may be more nuanced than we ever imagined. CRP asks us to see gravity in a whole new light. A theory must match the data to be taken seriously. When Roy applied CRP's math to real galaxies, the results were remarkable. CRP accurately reproduced the flat rotation curves using only visible matter. Unlike dark matter models, which can be tweaked, CRP's predictions come straight from what we observe. No invisible halos, no adjustable dials. The model's rigidity makes its success even more impressive. CRP has passed its first major test, standing toe-to-toe with the reigning dark matter paradigm. It's a viable contender in the quest to understand our universe. The journey is just beginning, but the evidence is compelling. Sometimes a new idea can illuminate the cosmos in unexpected ways. To understand CRP's potential, let's compare it to its main rivals. First, the ΛCDM model, the standard cosmology built on cold dark matter and dark energy. It explains much, but its key ingredient, dark matter, remains undetected. Second, MOND modified Newtonian dynamics, which tweaks gravity at low accelerations. MOND predicts galaxy rotation curves well, but struggles with larger structures and relativity. Now CRP. It modifies gravity based on mass density gradients, not acceleration. This subtle shift may let CRP handle both galaxies and clusters where MOND falters. CRP's advantage over ΛCDM? Simplicity. No need for mysterious particles. It works with the matter we can see. The ultimate test. Which theory explains the most with the fewest assumptions? The race is on, and CRP is a serious contender. The cosmos is the judge, and the data will decide. CRP's promise goes beyond spinning galaxies. If correct, it could solve two cosmic mysteries, dark matter and dark energy. CRP's repulsive force mimics dark matter within galaxies, no invisible particles needed. But it could also explain the universe's accelerating expansion. On the largest scales, sharp density gradients between galaxy clusters and voids generate a pervasive repulsive force. This could be the dark energy pushing space apart. If true, dark matter and dark energy are two faces of gravity's dual nature. One elegant idea could unify the mysteries of the cosmos. The implications are profound. The story of CRP is about more than gravity. It's about the spirit of science. Progress often comes from outsiders willing to challenge the status quo. Roy's bold question echoes the stories of Einstein and Wegener, outsiders who changed everything. Science isn't a set of facts, it's a method for questioning and testing. Dominant paradigms can create inertia, but independent thinkers keep the field vibrant. Whether CRP is right or not, it's already invigorated debate and inspired new inquiry. The universe is full of mysteries, and the next breakthrough may come from the next bold question. Keep looking up and keep asking why.